Thanks for coming to the tutorial today. And today I like to kind of take this opportunity to make a summary of I have been doing this type of problem for a couple of years. And I think it's a good opportunity for me kind of wrap up and to summarize several main results from some of my papers. So the topic for the tutorial is called simple heuristic for optimal inventory policies in supply chains. So, so here the next slides actually give us ideas why I think it's an important area to study. Again, as we know, in the supply chain, if we are looking at optimize the inventory decisions in the general supply chain, we know the form of the optimal policy in most of the supply chains is unknown. Okay, but the problem is the issue is still there. Okay, the manufacturer, the supply chain partners, they always have to figure out a way to increase the efficiency. So the problem is not go away. And even for the problems which we know how to deal with it, sometimes the exact optimization algorithm could be very involved. Okay, so I'm from business school, so sometimes we found sometimes it could be very difficult to try to convey these ideas or knowledge to MBA students, for example. So I've been thinking about, is there a way that we can make the system more transparent? Okay, so that's kind of the motivation. So these 3 and 4 are all related. Basically, I want to come up with the way, hopefully we can make the system more transparent, more intuitive, and easier to communicate with people who are interested in these areas. And something also related is the coordination issues as well. So I was, at the beginning when I'm interested in this project, I was hoping to have some simple solutions which people can use it as a target and come up with some coordination mechanisms. Because we know entire supply chain, it's not like one player only. There are many players involved. So something I found very important is that if you can find out some simple solutions that everybody understands, and hopefully based on that, we can come up with some easier coordination mechanism or contract that can help the supply chain efficiency. And the last motivation why I'm very interested in this topic is it's kind of like an ambitious, goal. In a sense that I know, as we know, the supply chain is composed of not just material flow, right? So there are many issues involved. For example, in most of the supply chains that we study, a lot of models ignore the financial flows. Okay, so one question that comes to my mind is that suppose we have some easy tools that we can use to optimize the supply chain, then maybe there's a chance for us to incorporate financial flow into this system, and then we can do something out of it and try to manage the supply chain in more efficient way. So I'm going to actually comment my last point in the end of the slides. In fact, I recently have some work to incorporate the financial flows to the existing multi-echelon systems. And I'm personally kind of excited about the result because once the student and we found that actually incorporate the financial flow problem does not mix up the system. We can actually come up with some structural optimal policies. And I will make some comments at the end. But anyway, these are the goals, kind of like the agenda for me, why I was have been doing this, because I have something that I want to resolve. So here is the basic model. So for today, I'm just going to focus on mainly this very simple supply chain structure. We call it serial system, in the sense that we have n locations in the supply chain. So the arrow represent the material flow. So we have stage n minus 1, and all the way to stage 1. And you can think of this person or this stage is the retailer who faces demand. Okay, and demand is stochastic. The setup is pretty much standard in the sense that every location has a holding cost. And here, Hn, H2, H1, these are something we call it echelon cost. So what is echelon cost? Echelon cost, you can think of that is kind of the additional holding cost when you move your material to the next stage. this marginal additional cost. That makes sense because when you move your material from the top upstream to the downstream, every stage you add value to it. So your holding cost should be increased. And that the difference, we use Hj to represent it. Okay, so that is something we call it echelon holding cost. And in a multi-echelon system, we normally assume there's a lead time between stages. So in this model, I have L1, L2, and so forth until Ln-1, Ln. These are the lead times. And for the basic model, we assume the lead time constant, deterministic constant, and so forth. So this is the basic model that I'm going to focus on for today. And we assume there is the RID demand between periods when there's a mean there. And the objective is try to minimize the average total cost per period time, okay? And in terms of information setup, so in the literature, for this kind of multi-echelon systems, sometimes we will study, there are like two ways to, we can separate all the multi-echelon systems into two categories. One is that we assume the information is centralized, in the sense that you can think of, there is a central planner who knows everything. I know the holding costs, I know the lead time, I know everything, demand information, etc. And my role is kind of like central planner. I'm the god of this system. I try to find out something we call centralized solution to it. So this is the centralized control. Or another setup that there's another literature talking about, what about the local information? That is the motivation saying that in the supply chain, not everybody knows each other, okay? However, still, we want to optimize the entire system performance. So in that situation, we call it local information setup. Now, in this talk, I will be mainly focused on centralized information, okay? And in some of my papers, actually, I also talk about the relationship between the local and centralized. And I will see if I have a chance to give a quick summary later on. But the information setup here for today's tutorial will be mainly focused on centralized system. And also, there are different ways to replenish your inventory. And in today's talk, I will consider both of them. So what do we mean by continuous review? Continuous review is that you should think of there's a computer system. This computer system can continuously monitor your inventory levels continuously. So whenever needed, the system will generate an order. So we call it continuous review. But there is another replenishment practice called periodical review system, which is very commonly seen in the sense that you can think of like schedule, right? Or MRP system. They always replenish order according to time, okay? And this is a system that I'm going to focus as well. So in this talk, I will talk about both of them. And as I'm going to show you later for the rest of the talk is that I'm going to come up with some same ideas which can be used to solve continuous review or periodical review systems. Okay? So the simple solutions that we come up with is actually the same idea can be applied to either continuous review or periodical review systems. And I'm going to demonstrate that in the next few minutes. Okay, so here's a little bit more detail. So for the continuous review system, we are going to assume Poisson demand, but the analysis can be carried over to compound Poisson. But for the demonstration, I will just focus on Poisson demand. And for this continuous review system, usually a lot of firms actually they implement something called RQ policy or echelon RQ policies because we assume we have a centralized information, so the system will operate under something called echelon RQ policies. So what do I mean by RQ policy? So in the supply chain, the system that I showed you earlier, we know every company is going to keep track of their something called echelon inventory order position and continuously. So if this echelon inventory order position is hit reorder point R for that specific stage, at that specific stage, that stage is going to place an order of Q. And this kind of policy, we call it echelon RQ policies. So in your mind, graphically, you should think of, okay, every stage, there's a computer to keep track of inventory order position, and as time goes on, demand coming in, it reduces. Once it hits the reorder points, the system generates order of Q, okay? And we assume there's a fixed order cost. I'm using kj, small kj for each batch. Q, I'm going to call it, so R is reorder point, Q is order quantity or batch. I'm going to use batch later. And we assume the order batches satisfy integer ratio constraints. So this is not just an assumption. People has already done some study that for the serial system, this kind of batch setup is more efficient among all other possibilities. So we assume upstream batch size has to be integer multiple of the downstreams. Okay? And the other system that I'm considering here in this talk is called periodical review system. As I mentioned earlier, we assume that so we assume that there is IID demand between periods. So technically, yes. So it's IID demand between periods, and every location implements something called ST policies. So what is S? S is similar to a base star level. Echelon base star level. And what is T? T is something like call it reorder intervals. So what is that? So if you are thinking about MRP system, for example, a lot of companies actually generate, a lot of MRP systems actually generate orders according to time. So my supplier maybe order every 4 weeks. And I'm the downstream, I order every 2 weeks, etc. Okay? So this T is associated with time. So that's why we call it reorder intervals, okay? And the base star level is something that the system wants to keep track of. So if you are thinking about, suppose T is equal to 2 weeks and base star level is 10, so basically every location is going to, that location is going to monitor the actual inventory level once it gets to 2 weeks and place the order up to S, okay? So that's how actual ST policy operate. And we also assume there's a fixed order cost. I'm using capital KJ for each T, okay? So if it's a shipping schedule, you can think of this KJ is a shipping cost associated with every 2 weeks, okay? And again, we assume that the reorder interval has to satisfy integer ratio constraint. So upstream reorder interval is the integer multiple of downstreams. Okay? So these are the basic setup. So I'm going to start with the continuous review system. By the way, before I move to the result, here are kind of a quick overview. So if you recall, my goal is try to come up with some simple solutions to the existing multi-echelon system. So in my mind, if you ask me what do I mean by simple, to me, I think these two problems are simple in the sense that they are single stage problems. So if we are talking about n equal to 1, and if you are talking about RQ policy, then this is the cost expression. Okay, for given R and Q, here is the long run average cost from the single stage system. So K lambda, sorry, this should be mu, but lambda mu, lambda is the arrival rate. K is the order cost. And this part, summation 1 to G, and divided to G, so that is the holding cost. And because if you follow the RQ policy, the inventory position is uniformly distributed between R plus 1 to R plus Q, so that's why you have the average cost form like that, okay? And similarly, if you are talking about ST policies, and this is the average total cost per period. So my heuristic is actually, I want to make a heuristic, as long as you have a knowledge of these two systems, then you are able to solve the multi-echelon systems, at least in a heuristic, okay? So these are the foundations to use the heuristic that I'm going to present to you later. But again, the heuristics based on the single stage problems. Okay, so let's move to continuous review system. So for the system that I show you, for the serial system that I show you, For given RQ policies, here is the way to evaluate the average total cost per period in the system. So this is a study from stage 1. Okay, so this is the stage 1 cost function, and it's kind of like recursively. You can get the total average cost per period recursively, start from stage 1 and stage 2 by plugging this recursion. Okay, and so here's something called O function. Basically, take care of the situations. If the upstream cannot satisfy your order, then you are using this O function to accommodate that situation. Okay. Anyway, so if you plug in this equation at the end, this C total C RQ vector is your average total cost per period. Okay, so that's how you generate. And so in the literature, we know that how do I find the optimal reorder point? So again, this R vector, Q vector is the decision variable, the control variables that we are interested. We want to come up with some simple solutions for these two vectors. Okay. So, but technically, if we want to know the exact optimal reorder point, here is the way. So it's kind of like a bottom-up recursion. So you start from solving the stage 1 reorder point, and you basically minimize this. So I have a head here. Basically, it's defined. It's kind of like uniformly distributed. So you minimize it. You got your reorder point, optimal reorder point at stage 1. You take this R1, plug in this function, and you generate your O1 and put it here. And then for the state, and you come up with your G2 function, and then you get your R2 star, and so forth, so on. Okay, so it's kind of like bottom-up recursion. You start from stage 1, stage 2. In every step, you get your optimal reorder point. You plug in, you got your optimal reorder interval. Reorder points for the entire system. Okay, so is this a very, very complicated procedure? The answer is no. It's not super complicated. But is that very transparent? It's not, because again, it's a recursion. Okay, so in my early work, I come up with some ideas. So in my early work, I've been thinking about, is there any way that we can make this thing simpler, and ideally we can put it in the Excel spreadsheet. So here is the first result that I got. So for the optimal reorder points, if you give me a fixed queue, if you give me a fixed batches, the optimal reorder point, Rj star, is bounded by the optimal reorder points of two single-stage systems. So what are these two single-stage systems? I have a very nice animation for you. Okay? So here is the system parameters for the lower bound system. Okay? So in the work, you will see lower bound systems is going to generate the upper bound solution. So what are the parameters for that? If you look at this, lower bound system cost parameters, Hj, so the holding cost is Hj, backorder cost is B plus, so this notation is the summation from stage j plus 1 to n. This is the summation of I from j plus 1 to n. And that's the corresponding backorder cost. And the lead time, again, this is the summation from I from 1 to j. Okay, so it's kind of, if you are at stage j, this Lj1j is equal to L1 plus L2 all the way to Lj. Okay, and batch size is given, again, it's given. So if I want to generate the approximation for it, well, the first result is that we found that the optimal reorder point for stage j, this guy is actually bounded by two single-stage systems. And these two single-stage systems are independent from the other stages. Okay, so that's very nice, because as you can see, to generate a solution bound, basically, I only have to solve the single-stage problems with revised system parameters. And numerically, we found that the gap is not big. It's pretty small. So in a sense that if you want me to pick a point to approximate this Rj star, I would say I will use like average or whatever creative, you get a weighted average out of it. You will get a pretty much good approximation. Okay? So that's the way we, so here is the theorem. So for every, for the optimal real point, Rj star is bounded by two RQ problems, single stage RQ problems. And we, based on that, we can generate some approximations to Rj star. Okay, so that's kind of when Q is fixed. This is how we generate the approximation for R. Now the next question is, oh sorry, there is one more. So this is a sentence, basically just to specify the parameters for the upper bound system. Okay, so for the upper bound system, as you can see, backorder cost the same, lead time the same, batch size the same. The only things that you get is that your holding cost is equal to H1J. So this is again summation I from 1 to J. Okay, so what is the logic behind this? Intuitively, what we are going to do is let's move back to talking about the intuition behind these two systems. What does that mean? That means that if you consider a supply chain, right? If we focus on the J echelon, so you have a holding cost H1 to Hj, right? So if you focus on echelon, and if you assume all the stages using the same holding cost rate. So remember before, if you look at non-echelon system, in the original system you have H1, right? H1, H2, H3, Hj, right? These are echelon terms, right? But if you extend every location to use the same local holding cost rate, then the whole system, because if you think about the entire echelon, we have the same holding cost rate, right? So what are you going to do? Are you going to put your stock in the upstream? No, there is no benefit for doing that. So what happened? What happened is that you are going to move all of your inventory to stage 1. And that's how you get the single stage approximation. Because once you move your material all to the stage 1, those L1 to Lj, these lead times would be together. So that would be the parameter for the total lead time, which is the sum of L1 plus J. Now, so my goal is trying to come up with the bounds, right? So if I want to get the lower bound, what will you do? I will just pick the smallest holding cost in this echelon, which is Hj. But if I want to come up with the upper bound system, what should I do? I should pick the highest holding cost, right, which occurs at stage 1, which is the sum of 1 plus, I from E, 1 plus 2 plus 3 until J, okay? So that's how you get this single holding cost. So in summary, how this idea comes from, basically, it's very simple. I just have all the echelon, every stage, use the same holding cost. And since all stages are using the same holding cost, there is no incentive to keep the inventory in the upstream. So all the material, optimally, you should move it to the stage 1, and the system reduced to a single stage system. And these are the corresponding parameters. So that's the basic ideas for the system. So we have already taken care of R, okay? So what about Q? Q turns out to be a little bit more complicated, okay? So we propose two heuristics for finding the optimal batch sizes. In the literature, Chen and Zhang in '94, they actually come up with the algorithm to find out the exact optimal batch sizes. But the algorithm is that they have to find out the solution bounds for each of the Q, and then they do an exhaustive search in the feasible set. Okay, so that's kind of the way they find out the optimal Q. And it turns out that computationally it's not trivial, because you have to find out the range for each of the Q, and then you do a search among all feasible solutions. So here, to me, I think there may be an easier way to come up with a good approximations for batch sizes. So here are the two heuristic examples. So we propose two heuristics for finding the optimal batch sizes. And these two heuristics are inspired by solving the following problem. So here is one problem. So if you recall, this CJL, this is the cost function that I take from the lower bound system that I showed you earlier. It's this function. It's this function. I use the lower bound system cost function because they are all independent, right? Now I have an n independent single stage problem, right? And for any q, for every given qj, I try to optimize its real point for that stage, right? So the objective function become a function of q only. And we can show that this is the sum of n separable convex functions. So it's not bad, right? And here the constraint side should be, original problem should be satisfy the integer ratio constraint, right? So let's try to relax it. So we just, instead of solving this integer constraint, let's just solve this linear constraint, okay, inequality constraint. And it turns out solving this problem is not that bad. There is something called clustering algorithms that can help us efficiently generate a solution, okay? So clustering algorithm is something, this is the typical like optimization problem. So basically it's a result of KAV conditions. But anyway, so if we solve this problem, then we can get a batch size, which may not satisfy the integer ratio constraint. So we have to do some, treatment to that, okay? But anyway, we have a way to convert the result of the solution into the satisfied integer ratio constraint, okay? So this is at the beginning, the heuristic for Q is coming from here, okay? We basically solve this. Now you may have a question, why I picked this? The reason is because, again, all of my work is, I need some kind of empirical investigation versus some theory, combination. So what I found here is, do you remember the recursion that I showed you earlier? This bottom-up recursion. Numerically, I found the shape, it's a convex function for every echelon, right? The shape is very similar to this guy. So that kind of gives me an idea, so why don't we just solve this instead of the exact function? And it turns out it's beautiful, it's very good, okay? Now, so my next step is that, okay, I know I have a way to generate approximation for Q, but can I further simplify it? It's kind of my next job, okay? So this clustering algorithm, for those who knows optimization, that's great, we can solve it, no problem. But now I want to present it to MBA students. How can I tell them, here is your clustering algorithm, go run it, and you will get the approximation? It's hard, okay? So I kind of thinking about this problem, so I actually come up with another idea to make the computation even simpler, in a sense that the solution from the cluster algorithm is close to the solution obtained from the following two-step procedure. So I'm going to introduce you two procedures. After you run these two procedures, you are going to get a solution, and that solution is actually near-optimal to the original problem. So here are the two procedures. The step one is clustering. The second step is called minimization. So what do I mean by clustering? Clustering is that give me an n-stage system. I have to, figure out a way to cluster some of the stages together. So what we found here is that by using the holding cost and the fixed order cost, I can cluster this. And this is the same idea, it's exactly the same as the deterministic problem. For those who understand, remember that power of two or related literature in the deterministic, when we want to come up with the power of two solution, we have to cluster stages, all that. And this step is pretty much the same. Although in one of my papers, I come up with some justification to say why we can use the deterministic approach to clustering. But in summary, the step one, all you have to do is, suppose this is a four-stage system, I have cost parameters, I have fixed order cost parameters, and all I have to do is connect these dots together, and I'm going to fit. So for this particular problem, I have two clusters. Cluster 1 contains stage 1 and 2, and cluster 2 has stage 3 and 4. And for the stages in the same cluster, they are going to use the same batch size. So that's after step 1, okay? So you give me a problem, you give me all the parameters, and I put in a graph. I can tell you, okay, for this example, you have two clusters. One is stage 1 and 2, and the second cluster is 3 and 4, and this cluster, the stages in the same cluster is going to use the same batch size, okay? So that's step 1. Now step 2, you may, yes?
Just one, are you still talking about the lower, sum of the lower bounding costs that you're minimizing?
Yes.
Or is this going back to the original problem?
So I'm actually, so this result is actually inspired by solving this problem.
Okay. So you're not talking about the clustering?
Yeah, clustering for this problem. So this is so I said the solution obtained from the previous solution is actually very close to the two-step solution. I have some theoretical justification in one of the papers, but the focus is the previous lower bound problem. But if you solve that, that is almost equivalent to do these 2 steps. One is clustering based on the holding cost, as I show you. And the second step is that, okay, now we have an idea which stage to be grouped together. The second step is that, then how do I generate this common batch sizes for each cluster? And here is the way. Again, it's all solving a single stage system. Maybe it looks like complicated, but let me explain it. It's actually very simple. It's a single stage based problem. So the notation here, Hn, is the holding cost, the sum of the holding cost, actual holding cost in that cluster M. M in the previous example could be 1, could be 2, but it's the sum of the holding cost in this cluster. And the same thing for K, okay? And here, I put a prime there. Prime, you can think of it's a local holding cost. Again, so this notation is the sum of the local holding costs in that particular cluster. So these are the parameters that you should use to generate this common batch size in the cluster, okay? So then once you have this system parameter, all you have to do is, again, just solve the single stage problem. How? So this is remember at the beginning I showed you a single stage problem cost function, right? So here's the lambda demand rate times K in this cluster, plus here is the single stage formulation, right? Divided by Q. And this Q is the batch size that you should use for that cluster. Of course, you have to subtract, because we are going to enforce the integer ratio constraint, right? So this procedure starts from the smallest cluster, C1. You generate a Q for C1 cluster, and you make it a constraint, and you solve the class 2 problems. And all the way, depending on how many clusters you have. In some situations, if you have one cluster for everybody, that's good. You solve one time. In some situations, in the maximum number, it will be n cluster, right? Everybody that's separate, right? So in that situation, you solve at most n single stage problems, and you will get a approximation for Q, okay? Okay, so yeah, here are the way that basically just give you an idea how this single stage results, okay? So for this problem, we can have 2 variants. One is, we call it heuristic one, but it's kind of like one variant in the sense that if you look at this is the purely the lower bound cost functions that I get from that cluster, right? So these are the lower bound cost function within this cluster, and I sum all of them. And for this cost function, again, it's a convex, I can find the best corresponding real point and use it plugged in the objective function. That's one way. And the second way is kind of like slightly a modification on this, in the sense that we can actually solve a real single stage system in the sense that here is the single stage system I suggest you to use. Instead of using the sum of, so the difference is this part, okay? So if you compare heuristic 1 and 2, the difference is this part. One is that in the previous one, I just used the sum of those lower bound functions in that cluster. Here, I specifically tell you that for this cluster Cn, here is the single stage function for you to use. And again, you based on this, again, as you can see, you still have a single stage structure, holding cost, back order cost, and the demand during lead time, some kind of demand during lead time. And then based on that, you find your best reorder point, and you take the problem, you solve the single stage problem. And you start from the lowest cluster all the way up. And how good is that? So here's the result. So this is the one, I think in one of the papers I compared various parameters. And I don't really remember what do I compare, but I just remember there are a lot of computations going on. But here is the example. So in variant 1 is the heuristic 1 that I show you. Variant 2 is the heuristic 2. The only difference is that even the single stage cost function, that is the only difference. As you can see, both heuristics are quite effective. So among these 512 examples, if you are using the procedure that I'm telling you, like 2 steps. One is that you cluster. The second step is that you solve the single stage problem from cluster 1 all the way up to the last cluster, and you get the batch size. And then these are the corresponding performance. So when penalty is big, backorder cost is big, you can actually get, it's actually very effective. Out of 112, you get about like 300 optimal solutions. I'm talking about optimal solution, is that 100, okay, so it's no error. And if you look at the majority of the cases, you say most of the case, you are going to generate a solution almost less than 2% for most of the cases, just based on that procedure, just solving single stage problems. Yes?
That's interesting you mentioned the EOQ heuristic, because in a way, what I was thinking before you present is that if you have this lower boundings completely separable, then you can resort to finding that if you take EOQ with RQ policy together, it's still quite okay for single echelon model that is confirmed by your results.
Exactly.
You
So
have better results, but EOQ is not too bad.
Exactly. You are absolutely right. But here, the EOQ solution, I want to emphasize that this EOQ solution is different from the power of 2 solutions. So this EOQ solution is basically, I take that minimization problem that I show you, and again, there's a very important step to differentiate this EOQ solution versus the power of 2 solution. Power of 2, we know that you get a solution, right? And you turn it to a solution of power of 2, right? But this EOQ solution in my paper, actually, I try to promote the ideas that I show you. You start from stage 1, you get a Q first, cluster 1. You get a Q for cluster 1, and then for the second cluster, you solve a single stage problem subject to the integer multiple of Q. And that is the solution that I come from. So if you're using that approach to generate the integer ratio solution Q, it could be very effective. However, if you take the same problem, plug in the power of 2 solutions, actually the average performance is not that good. And I don't know, maybe most of you know it, but the power of 2 solution in general may not be effective, right? We know power of 2 is used to prove the worst case bound, right? So the average performance may not be good. And the procedure that I propose here is actually the average performance is better than the powerful 2 solutions, okay? But again, so the key message here is that, yes, if you are solving the deterministic problem, and if you have a better way to generate that integer ratio solutions, yes, the deterministic problem could be very effective here. Okay, so that's some of the results, which I didn't show you in the previous slide. But if you are interested to look at this further, I think it's in the 2008 paper, I think. I don't really remember, but it's one of the papers. Okay, so that's the RQ, continuous review system. It starts at 1:30, so it should be 3, right? Okay, good. Yeah, I thought it was like 2:30 or something. I still have a lot to go over. So now let's turn to the periodical review system. And interestingly, so the reason why I start thinking about this ST policy is actually inspired by one of the students in my class, MBA class, executive students, who actually is a manager in EMC facilities. Okay, so the company actually had a contract with UPS. And so in their contract, it's kind of like third-party logistic type of contract. So the UPS actually charged them some fixed fee. And the UPS is going to send out a truck to their facility every Tuesday and Friday. So it's kind of like based on the T, right? So the manager actually come to me asking, how do they determine Tuesday, Friday? And why do I have to pay this amount of money? So do you have anything to talk about, like, literature? And I learned a little bit like EOQ or power of two deterministic. But when I come to the stochastic model, it turns out there's not much ST policy, especially in the multi-echelon setting. In the early work, we do have a literature on the ST policy for the single stage system. But when we move to the multiple locations or multi-echelon systems, most of the papers are focused on RQ system. So that's something like, I'm a little bit puzzled why there is no paper on this area. So I thought it might be cool, if we can come up with something to deal with it, So at the time I started the project and I wrote a few papers on this so-called ST control. So I'm going to introduce it to you, some of the main results. But let me kind of give a quick review on what this policy looks like, okay? Because ST is less familiar to us. So if we consider a two-stage system, this is a very simple case in the sense that, okay, stage 2 upstream has a reorder interval 4 weeks, and stage 1, the reorder interval is say 2 weeks, okay? And both of them have the lead time. Stage 2 has the lead time 2, and stage 1 has the lead time 1. Suppose we run this system. So what exactly this policy look like? Again, so here's the time frame, right? So we are kind of moving the time t plus 1, 2, 3, 4, 5, and so forth, so on. And this is the inventory position, echelon inventory position for stage 2 and for stage 1. And this is the corresponding net echelon inventory level, okay? So if I run this, we are going to see actually the decision that I made. I forgot to bring my remote. So the decision, so in this system, basically the time that you make for stage 2 at t will affect the cost within this period, okay? So how does it create it? So if I make a decision here at stage 2, because the lead time equal to 2, right? So the shipment won't arrive until this point, right? And once I get to this point, this is definitely affect my stage 1 decision. And then since I don't have another chance to order for stage 2, so whatever left over, the stage 1 is going to order it again here, okay? So in other words, I'm the stage 2, I make the decision here, and my decision is actually affects my stage 1's decision in these 2 points. And all these decisions is going to affect the corresponding cost. So in a sense that since we are interested in the long run average cost, so what we can do is that if we can analyze this so-called the regenerative cycle, then we are able to evaluate the system cost. So when I started the project, so the Shang and I, co-author, we actually carefully characterized the inventory variables in these time periods, and we propose the results at the end. We come up with the algorithm. Again, it's more like a bottom-up recursion, okay? From stage 1, 2, 3, 4 until the stage n. And if you plug your parameters in this recursion from stage 1, so here, as you can see, this G1 function, this is the stage 1 cost function, which is equal to, since we are interested in the average total cost per period, right? So I divided 1 divided by T1, okay? And this is the sum of the holding cost incurred during that T1 period, okay? And I saw this recursion here, and here is something very messy, but it's a recursion function that you can use. And then, and this is the holding cost part for that stage J. And then if you run this, you can evaluate the system cost. Now, in terms of the optimization, what we found here is that if you give me a set of t, okay, if you give me the reorder interval for all stages, actually I'm can find the optimal baseline level for you, okay? So the procedure is kind of, again, from stage 1, and from stage 1 I have a cost function, and I find the minimizers for given one, the T1. I can find the minimizers, and I plug these minimizers here. I generate the stage 2 cost function, and I minimize it again, and I repeat this procedure. Okay, so at the end, I can find the optimal base star levels for fixed t. And so the same question repeats, right? So the question is, how, okay, so here's the holding cost and echelon, okay? So I know how to optimize S. But is there any way we can make this computation simpler? Again, so we found that, again, we can approximate that base star level by 2 single-stage systems. The logic is exactly the same that I mentioned to you earlier. If you enforce all the stages using the same holding cost rate, the whole system would break down to single stage. So these are the corresponding single stage cost functions. For the lower bound system, generate the upper bound solution, the holding cost is exactly the same. So the holding cost, that you just pick the cheapest one, the smallest holding cost in your echelon. And the backorder cost rate here, lead time, since there's no incentive to put the stock in the upstream, so all the system break down into single stage, and this is the cumulative lead time from stage 1 to J, and for given reorder intervals. And similarly, by picking the most stage 1 local holding cost, I can generate another upper bound system. And for each of the single stage systems, I can find the best base star levels. And we can prove that the optimal base star level is bounded by these 2 single stage solutions. So we have an easy way to come up with approximation for base star level. Now, so this is not too exciting, and we pretty much can predict that, right? Now, what's more exciting is how do we give the heuristic for optimal reorder intervals? And I think this is the I think I have this paper in OR 2010, and I think I personally think that this is the best work that I have in my life, although not many people, so far. Although not many people know there's a result like that. But I really enjoyed this piece of work, and I want to share with you. So again, I'm going to tell you how do I generate approximation for optimal reorder intervals. So if you go back to the earlier formulation, as you recall, in this previous slide, I said, okay, if you give me a t, right, I can find out the optimal base star level, right? So finding the base star level is not a problem, okay? So our question is, how do we get approximation for t, okay? So this is the problem. As you can see, if you use the optimal base star level for that given t vector, then here is the total cost function for you, okay? But something that you should notice is that this gn function is a vector, is a recursion, right? So it's a function of t1, t2, t3 until tn, okay? And our problem is try to solve, so this is our problem. We want to minimize this, try to find out the optimal t such that we satisfy this. And this problem is very hard to solve, okay? We have the optimization algorithm to get the exact t, the optimal t. Yes?
Mark, you are not going to tell us the same approach as you explained for the Qs.
Say it again?
No, you had this particular approach to determine the Qs, these sums of the lower bound.
Yeah.
Are you not going to do exactly the same?
You actually, you have already predicted like a few slides ahead of me, but but I'm going to show you a very neat idea that I like, and that idea will actually help us to lead to that result that you point out. But here is the idea I'm going to show you. This is the original problem, and in the next few minutes, I'm going to tell you how do I turn this problem become solvable in the sense that it's a sum of n separable convex functions. And so here's the idea. The idea is that at the beginning, I'm going to decompose the system total cost to each of the stage. I'm going to allocate, so here is the system cost, like a big pie. I'm going to present you a way to allocate the total cost to each of the stage, okay? So that's step 1. So I'm going to make the problem like that. Originally, it's a recursion from stage 1 all the way to stage n, right? So it's kind of system cost. The first step is that I want to allocate the cost and put that cost to each of the stage. So it becomes a small g, okay? So small g here in my notation wise, this is the total cost for each stage. And this capital G is an echelon. So I'm going to do this, and then I solve this problem, okay? And the next step is that I want to derive two systems. One I call it lower bound, the other one is called upper bound. And then I'm going to make this system. Again, if you notice, this is the vector of Tj, which is T1, T2, T3, all the way to Tj. Then I want to make it like this. It's only a function of Tj only for both problems. So I'm going to share with you how do I come up with these two systems, okay? And once suppose I can get to this stage, then again, let's go back to Tom's question, right? It's not that bad to solve this. So let's see how do we get there. Okay, so first step is try to decompose the total system cost function. I borrowed the old literature, there is not old literature, old concept called induced penalty cost function introduced in Clark and Scott. And we found that there's an induced penalty cost function still to this problem as well, to ST problem. So Clark and Scott's little paper in 1960, you can think of in their model T is equal to 1 for every stage. And here is the general T, okay? So we use the induced penalty cost function Pj to decouple the system cost. So here's the idea. I'm using two stages as an example. So this is the stage 1 cost function, G1, right? So this is the function by itself, okay? And here is the convex function, and I know you give me T1, I know what is the best base star level, good. So I decouple this convex function into two pieces. One is by itself, and I'm going to leave this one to stage 1, and then I'm going to give this induced penalty function in the sense that this is the penalty cost that I charge to stage 2 if the stage 2 cannot satisfy with my demand, okay? So I'm going to charge this one to stage 2. Very nice, right? It took me a long time to do the animation, so I'm going to spend more minutes on this slide. And then here is the holding cost itself, right? Stage 2. So you sum them up. So this is going to be a convex function again. So this is the stage 2 cost, okay? And then based on this procedure, I can decouple it again, and I can send the induced penalty function to stage 3 if there is stage 3, okay? So this is how I decouple it. So at the end, this is the way that I allocate cost. So for any given epsilon j cost, I can somehow make it like a sum of stage 1 cost. But the problem here is, again, if you notice that this here is still a vector, okay? Even though I do this kind of treatment, I still cannot decouple my decision in the sense that my stage 2 cost, my stage cost still depends on my stage 1 and 2's reorder interval together. So I haven't really get what I want, but at least this is the first step. Okay, here's the echelon cost. I find out a way to, here's yours, here's mine, you know, we try to set it up. Although the stage cost function is a vector of stage 1 to j, okay? So that's the first step. Now, how do we construct the bounds? So here is the nice results that I like to share with you. So this is the graph I showed you earlier, right? So this piece is the same. For stage 1, I charge the induced penalty functions and so forth. Now, what we found here is that for this induced penalty function, again, it's a vector of T1 and T2, right? What we found is as follows. Let's define Gjj is Tj. Oh, sorry, not G. Tjj is a vector of Tj. So in a sense that this notation, suppose this is T22, that means that your stage 1 and stage 2, both of us are using the same reorder interval, T2, okay? And another notation is this. So it's Tj1. So if T21 means that the stage 2 using T2 and the stage 1 using the minimum reorder interval, which is 1, okay? What we found is as follows. We found out that if the stage 2, when the stage J's downstream stages using the same reorder interval as Tj, the resulting penalty is the lower bound to the original. So graphically, This black line is the original induced penalty function, which is a function of T1 and T2. And what we found here is that if I'm T2, you are T1, but if you downstream use the same reorder interval as my T2, then we can generate an induced penalty function, right? So this will be the lower bound. On the other hand, if you are the stage 1, you just use 1, nothing else, you use 1, then the resulting induced penalty function is the upper bound to the original. And I think this is the result that I'm very excited. And intuitively, it also makes sense. So I'll give you an example. Suppose I'm a stage 2, you are the stage 1, and let's say I'm T2, right? So I'm saying that I have my reorder interval is 4 periods. So for your option, you can choose 1, 2, or 4, right? So what I'm saying here is that if you are using 4, then the induced penalty function that you charge to me is the minimum among all possibilities. So what is the intuition? That means that so let's go back to the definition of induced penalty function. Induced penalty function meaning that is the cost. I was penalized because I cannot satisfy your demand, right? You are stage 1, I cannot satisfy you, penalize me. So in other words, if I'm using 4, you are using 4, the penalization is smaller. Why is that? Because remember, if you are using 4, right, you aggregate 4 periods of demand at a time, ship it to me, right? Because you aggregate 4 periods of demand together, the variability is smaller. I should say coefficient of variation is smaller. And that smaller variability is actually the reason why I have a smaller penalty. Because I'm upstream, if you aggregate 4 at a time, I have better ideas how to satisfy it, rather than you send it like 4 times. Yes?
It will also be because if you use 1, that's the maximum number of times you can get an induced penalty cost. It's not only the variance, but also the fact that you can charge at 4 different moments in time. You may be charged with penalty costs. Because there are four moments where you can be more or less induced to stock out or not.
But this PJ I didn't show, it's an average per period though. Okay. I didn't really give but this PJ it has already taken into account that it's not like 1 versus 4, it's all ones, it's all average number, yeah. But I think the main key takeaway is that if you are using the same reorder interval, then the same as mine, I have a bigger, right? So you send it out all the time. I'm your upstream. I know better how to satisfy you. And that piece of is very important because we can get this. So what do we have? Here is our the original induced penalty cost functions. This is the TJJ. What is TJJ? It's everybody using the TJ, right? So this is actually the function of TJ only. And what is this guy? This guy is 111 to TJ, right? Again, so it's a function of TJ. So, and that's it. I think that's the way how I make these things. You know, so how do I construct the upper bound system? I basically just take this upper bound penalty to the stage 2 and sum them up. And I'm using this lower bound to generate the lower bound cost. Okay? So graphically, here's an example to show you how tight it is. So the blue line here in the middle is the induced penalty function when I using t equal to 2. So in this particular example, I think I didn't say it here, but in this example, t2 is 4, okay? And I show you the induced penalty function for different t1s. So you have 3 options, 1, 2, and 4. And if you are using 1, the red line is the induced penalty function here. If you are using 2, it's here, 4 is here. So if I'm T2, I'm using 4. If you pick 4, then that's the lower bound. And the red line will be the upper bound, okay? And since it's so tight, because we are talking about variability benefit, right? So since it's so tight, so the cost function, so the heuristic here, I'm using the upper bound. So as you can see, this becomes the function of TJ only, the sum of TJ, okay? And solving another problem is a lower bound problem, which I just using the lower bound of induced penalty function. And again, I can relax the constraint, become the inequality, and then I can solve it. Okay, so I can we can generate the solving both upper bound and lower bound problem, and we apply the clustering algorithm again, and then the heuristic solution, we just pick whichever yields the smaller cost. And so the idea that I showed you earlier, how do we generate the lower bound, cost bound, etc. They actually help us to come up with an algorithm to find the exact T star. Okay, so we can compare. But I didn't go to detail in the talk. This talk is more focused on the heuristic perspective. Okay, so that's the way to do this. And I didn't say it here, but we also say something in the paper. Actually, the idea that I show you to restrict the downstream player using the same control parameter as yours, that idea is actually can be applied to the RQ problems. And it turns out, if you using that idea to deal with the RQ problem, and we can figure out a way to construct the optimization algorithm to solve exact optimal Q, right? And that algorithm is actually more efficient than the existing in the literature. We kind of do some numerical comparison in the paper, but I didn't mention here. Just so you know that ideas to decouple to construct bounds can be applied to ST and also RQ for this problem. Okay, so this is the heuristic. And now, again, something that although we are able to generate some solutions, right? Now go back to Tom's question. It seems to be intuitive if we can, just take those simple stage approximation and so forth, and to do a minimization. That maybe work out well, right? So what we found here is that we actually found out this lower bound function that we generate, in terms of the shape, is actually very similar to the lower bound cost functions. So here comes to the second heuristic. Instead of solving this complicated one, you have to decouple this and that. You can just take this lower bound. I'm using H, but this is I copy paste from my paper. But here you should think of it as L. Okay, so it's holding cost, backorder cost, and I plug in and solve the relaxed problems, and we actually come up with another heuristic. Okay, so that's I think it also I couldn't really remember, but it turns out this approach is not too bad either. Okay, I think this is in the OR letters in which 1 year I forgot, but somehow we test it, and this idea still work well. And then now my prediction is that I still can use that, since I have already get to this stage, right? So I think it should be if I want to apply the two-step optimization procedure that I show in the RQ problem, I think that should be work out well as well. But I didn't test that. So, but just so you know that at this stage, in summary, what we have here is that no matter you are RQ or ST, we are able to give you a very simple ways to speed out the solutions. Okay, and that's the IID system. And now, I guess when I start with the PhD until this moment is about the year of 2008. So in the year of 2000, I'm just thinking about whether I can expand this simple stage-based heuristic to more realistic system, in the sense that what about there is a non-station demand? What happens? So the next few minutes, I'm going to give you a quick summary to tell you the short answer is yes. The whole idea is this single stage approximations here and there can be a carryover to non-station demand system, and here is the example. So what do I mean by non-station demand? Why it's important, of course, right? Company has some seasonality, trend, business cycles, etc. And the non-station demand complicated inventory decisions, in the sense that if we are trying to minimize the total cost in a finite horizon, the standard approach is plug in a dynamic program, and then we do some recursion from the last period all the way up, right? And this problem for the non-station demand case is more complicated than IID. Is that in the IID system, you can say that, okay, more or less every period you do the same, right? So it can be think of, it's kind of like you are solving a regenerative cycle. But in the non-stationary domain case, it's not the case, right? So if we want to solve the serial system that I show you at the beginning, when the domain is non-stationary, then we have to do a dynamic program, and you have to solve, like, starting from the last period, you find a optimal base star level, and then you move to the next period, etc., all the way, right? So it involves time and also stage. So it's going to be even more complicated. So how do we come up with the simple solution to resolve this issue? So here is the, I actually have a slide to, so CS is Clark and Scott. Okay, so Clark and Scott show that if domain is non-stationary and time-varying echelon base star level policies are optimal. So let's say S, so this is the base star level, SJT, is the optimal echelon base star level for each stage. So how do we come up with this optimal base star level? So it's that every stage reduce your echelon inventory level and order up to this. So this is the way how do you run this policy, okay, base star. And how do we get this base star policy? Again, I kind of give you a quick summary already. So your optimal base star level can be obtained by solving J sets of dynamic programs recursively. You found the stage 1 for each T, and then after you know this, you can generate an induced penalty function every period, and then you plug in your DP and you solve your stage 2, etc. Okay? So it's quite complex. Okay. Now, the main results I want to share with you is that even for the non-stationary demand case, we can we can come up with a simple approximation for every T by solving n sets of single stage problem. Okay, so how do we do that? Okay, these are the main results. There's an analytical approximation. I'm actually going to present this talk tomorrow morning at 8 o'clock. So if you are tired and if you come back, there's a talk for it. Okay, so here is the main result. Let me get to the point. Okay, so how do we construct the solution bounds? Again, we start from every echelon. So for every echelon J, we can construct the upper bound system by restricting the stage I to always order up to the echelon inventory level to your upstream stage. So this idea is slightly different in the sense that how do we get the upper bound system? What we have here is that, okay, I have a multi-echelon system. Now I want every system, every stage to order up to the echelon inventory level of your upstream stages. You order as much as you can. So before, we know in the classic echelon inventory policies, you just order to some ideal level, right? And if your upstream has a lot of stock, you don't order. You just keep it in the stage 2. You just order to the level that, ideal level to you. But here, in order to construct bounds, I changed the policy. I said, look, you just order whatever your upstream stage has, as much as you can. And if you do that, of course, as you can imagine, all the material is going to, move, every period. So all the stages more like the pipeline, in transit points, They don't carry over. And the result will be kind of like a single stage. It's a resulting solution from the way the policy that I suggest become a lower bound So after you do that, the whole thing become a single stage, And you have the result, you have a solution for that system. And the question is whether that solution is the upper bound to the exact one. Okay, so that is something that we don't know. But here, that is kind of like the idea. How do we construct this upper bound system? And same thing, construct a lower bound system. The idea is slightly different in the sense that we are going to restrict the holding cost of the downstream stage, and this Ci is the ordering cost. We also enforce the order cost equal to 0. And in that situation, of course, I want to optimize it. If all of my downstream, there's no cost, No holding cost, no ordering cost. What's the point to keep it in upstream? No, you won't, Again, so the optimal policy says you are going to order as much as you can. So again, the resulting system is more like a single stage. You just keep moving your material all the way to stage 1. And that's ideally is similar to single stage system, right? So the question we want to answer is that is the resulting solution from the idea, from the lower bound single stage system, is the upper bound in every period? That is something that we want to know, okay? And so if I do that, whether that system is equivalent to the single stage system, yeah, we kind of feel it because the material just keep going, right? So stage 2 to stage n is more like a pipeline in transit, right? So it's likely it could be a single stage system. And what are the resulting parameters, if so, okay? So we try to answer it. So the main result is that, yes, for the lower bound system, from the upper bound system, we can generate the lower bound solution. And this lower bound solution, SJLT, can be found by solving a single stage system using the notation for every stage J, and the parameters look like this, okay? And these three is similar, is the same as I show you in the IID situations. Holding cost, I'm using the stage 1 local holding cost. Lead time, tau is, in this page, I mean, you know this is the total lead time from stage 1 to stage J, okay? And this penalty cost is something that exactly the same as I showed you earlier. But what's interesting is this term. The ordering cost becomes this, okay? So in other words, in order to solve, I can construct a single stage, and that single stage has these parameters. If I solve that single stage problem with these parameters, I can generate a base level in every time period, right? And that solution is the lower bound to the exact optimal. And similarly, if I pick the, similarly, if you recall, how do I generate the lower bound system? I basically restrict the holding cost and purchase cost equal to 0, right? So all you have to do is you just change those downstream ordering cost to C and holding cost equal to 0, and you get another parallel, which is the lower bound system. And if you solve this lower bound system, you also generate the baseline levels, and those solutions, SJU is the upper bound to the original exact optimal solution, okay? And how do we get a heuristic? So tomorrow in my talk, I will provide a little bit more detail why, like intuition, why, the intuition behind all of this, okay? But here I want to skip it, just so you know that the same single stage idea can be carried over to non-stationary systems. And how do I generate a heuristic? Again, I'm just taking the weighted average of these parameters, right? And then I can solve the single stage system in a finite T horizon, and I can get a solution. And how good it is. Here is a two-stage example. So the total number of instances is 960, and we are just focused on stage 2 solution itself, and we define the error is equal to the exact optimal minus this approximation, okay? And divided by optimal solution. As you can see, this number means that how many optimal solutions that you can generate by changing your weights, okay? So, and this is the average percentage error. So what we try to do is, how do we know the weight, right? So I say it's weighted average. And I guess this slide just try to address under what is the weight the most efficient. So it's kind of, I'm also curious, so we try to do, okay, weight equal to 0, 0.1, 0.2, 0.4 until 1, right? So when your weight equal to 1, this is the lower bound solution, and this is the upper bound solution, and these are the solutions in between. Okay, what we found here is when penalty cost B is bigger or the service level is higher, actually if you are using, somewhere like 0.4 to 0.8, 0.9, the performance are pretty good. And in the backorder code, when backorder code B is smaller, service level is lower, then your solution should be slightly close to your lower bound solution. Okay, and that makes sense. If your penalty service level is bigger, then you should increase your stacking level. So your solution should be slightly close to move to upper bound solution, and so forth, so on. Okay, but in general, I guess this numerical study tells us that in general, if you pick a solution, you pick your weight somewhere around 0.4 to 0.9, depending on your service level, it's quite effective, even in the non-stationary demand case. And of course, in this set of numerical study, we test different form of demand. It could be increasing, could be decreasing, could be concave, convex. We test all variants, and this is kind of like the summary of the results. Okay, and so we suggest a table like that for you to use. Suppose you are, here is your service level. If your service level is about this range, these numbers look good, at least from our numerical study. Here is a table for you. You may consider to use it. And we also do the same thing to test the 4-stage systems, and it's also all very effective. Okay, and then why it's so nice to have that result? The result is that we can actually borrow some myopic solutions to the finite horizon problem, right? So even to solve the single-stage problem in the finite horizon, you still have to plug in dynamic program to do this and that. But we all know that in the single-stage systems, the myopic solution is quite effective under some parameters, under some conditions. So that kind of motivates us that, okay, since we have a single-stage approximation, right, for every location, and we can do further work to make it simpler in the sense that let's just convert everything to myopic solution. And these are the myopic solution results. So for MBA students, I actually have some very nice, clean equations to show them. Look, if you have a non-station demand, here is how you should choose your base star level when T change along the time, okay? So this covers the average demand, right? From T, or here I'm counting the time backwards. So this is a T to the future L period, okay? So you should consider the lead time in the next L periods plus some safety factors here, and these are the corresponding parameters. Now, again, this is the myopic, right? But for managers, well, I can easily use it because I know as time move on, if you have some seasonality, demand go up, you should adjust your base star level accordingly, okay? And this, if you are interested in the local base star level, so this is echelon, right? So the difference is the local base star levels. So so from here, we can do some sensitivity analysis to get some insights. So I will tell you, okay, if you are the manager at stage J, all the way up in your upstream, here is the pipeline inventory that you should stock, like pipeline inventory plus safety stock, which is the difference of this. And again, I think in the papers, we also try to generate some insights from the myopic solution. But just so you know that once you get to the single stage results, we can use the myopic solution to tell many stories to managers. Okay, and I'm a little bit tired, so I want to remember at the very beginning, there's one motivation, right? I bring up, say, okay, if we have a simple solution, how can we come up with a simple contract to at least to make a system coordinate. So we have some near optimal coordination scheme. And this is particularly interesting for the finite horizon problem. Okay, so in the finite horizon, if we want to introduce the contract, is that a way that we can provide a simple contract? What do I mean by simple? Ideally, I hope the contract is time consistent, right? In the finite horizon problem, since the optimal base star levels change, right, all the time. So, it's possible to introduce a contract which is like time varied, but it's not critical, right? How do you tell the company, okay, for the week 1 to 5, here's your contract perimeter. From week 6 to 7, here's your perimeter. It's just not very easy to use. But since we have some simple solution coming out, Actually, in one of the papers, we introduced a time-consistent contract parameters, which can help us, we can coordinate system to the heuristic solution that I presented to you. Okay, so so here are the some comments. Okay, so and simplify the computation, this and that. Okay, now for the last 5 minutes also, I just want to show you. So far, we only focus on single-stage systems. Serial systems. But based on the existing results, for example, like assembly system, Professor Kai Russell actually has a very elegant. It's one of the main results in the assembly system. We can, under some conditions, we can actually make the assembly system to the equivalent single-stage serial systems. So if we have that relationship, I think we can take these simple-stage results to assembly system. And the distribution system is something that I'm still working on. So yesterday I have a talk, giving the algorithm I have a talk on focus on the distribution system under a location called virtual location policy. It's one of the allocation policy that was used in the literature. Anyway, for that paper, we actually come up with a way to find out the exact optimal solution, S and T. Okay, so that distribution system is under ST control. And now I'm at a stage trying to come up with to see if there is a simple solutions, again, single stage based, to deal with this distribution system. And the paper in the last part of my talk is focused on non-stationary demand, right? For base stock. But recently, there's a paper, again, it's a non-stationary demand system, and they assume there's a fixed batch sizes for every location. And those stages follow the integral ratio constraint. So it's kind of like similar to RQ problem, but it's in a finite horizon. And they show that, yes, for fixed Q, the RQ policy is optimal for the non-stationary demand case. Of course, the reorder interval, reorder points is also non-stationary. It's time, associated with time. And I look at the paper. I didn't do that, but I know my result can be applied to that RQ as well. And so the next few is more like challenge. There's a assemble to order system or general network, right? So suppose your supply chain is composed of a tree structure. Do you have a simple way to deal with it? And what about the non-stationary demand with fixed order intervals? All these questions are open, and hopefully me or someone will be interested in continue this work to do this. And in the last point, if you remember in my first slide, I said all these simple solutions, hopefully I can deal with more complicated problems. And for that, I show you we recently have a work on incorporate the financial flow into the multi-echelon systems. And the talk is actually 4:30 this afternoon. Actually, as we show is that under some financial payment policies, solving this joint decision like inventory replenishment and cash payment can be converted to multi-echelon systems. Okay, so and then obviously all of the results that I show you today can be bring up to that joint decision problem. So so it's kind of like at some level I kind of like achieve some objectives that I want to do at the very beginning. Okay, so still I guess that's the end of my talk. Okay, thanks for your patience. I'm very tired, so I hope you. Okay, thank you.